Hi, my name is Emma, and this is my presentation for Physics Lab 1. In this lab, I studied the motion of an eczema marker to determine if a computational model could accurately predict real-world constant velocity motion. The purpose of this lab was to observe the one-dimensional motion of an object, extract data from a video using Tracker, and then create a computational model based on physics principles. By comparing the observed data to the model, I was able to test whether Newton's second law, in the case of zero net force, could accurately predict the marker's motion. This lab was guided by Newton's laws. Newton's first law states that an object at rest stays at rest, and an object in motion continues at the same speed and in the same direction unless acted upon by an unbalanced force. Newton's second law says that an acceleration is directly proportional to the net force acting on an object and inversely proportional to its mass. If the net force equals zero, then the acceleration is zero, and both momentum and velocity remain constant. The observed position results were very similar to the predicted position data from my computational model, but the predicted and observed data showed nearly a linear increase in position versus time. This means that the marker moved with almost constant velocity with no significant acceleration. The computational model accurately represented this real-world constant velocity motion. For my experiment, I rolled an expo marker in a straight line across the table, keeping the camera fixed in place. I placed a meter stick in the frame to serve as a calibration scale, and I recorded the motion from a horizontal view aligned with the stick. After recording, I imported the video into Tracker and analyzed it to extract position versus time data. My system was the purple expo marker, and the surroundings included the table, gravity, the normal force, and air, so essentially everything else. Here I just included the columns of my results and also a photo from Tracker, and I took about 31 frames, and the initial time was 0 seconds to 1.03 seconds. And I also added a graph of the data, and it's near straight and constant, which means constant velocity. The initial start time was 0 seconds to 1.03 seconds. The initial position was 0 meters. And then the initial velocity is equal to the average velocity in this case, which was 0.436 meters per second in the positive x direction, which was found using the formula I listed above. I just put those initial values into WebWorks, so the position and then the initial velocity as well. To model this, I used WebV-Python to write a code that simulated constant velocity motion. The code applied Newton's second law with the net force set to 0. This meant that the marker's velocity stayed constant throughout the simulation. The program output both position and velocity versus time graphs, which I later compared to my Tracker data. So these were some of the data results. So the velocity versus time was a straight line, which meant that there was no acceleration. And then when you compared position versus time, it was a very linear graph, which again shows that there was a constant velocity. When I plotted and the predicted results and the observed results in the same graph, they overlapped almost perfectly. Both showed a constant slope, which is evidence of constant velocity. The only differences were very slight deviations that can be explained by experimental error towards when time was later, and was very slight deviations. The predicted was the red line, and then the observed position are the dotted points. Possible sources of error in this experiment included air resistance, rolling friction between the marker and the table, and human error in clicking points in Tracker calibrating the scale. These small errors explain the slight differences between my observed data and my predicted model. Of the axes were reversed, and the position values would be negative instead of positive. This would make the slope of the line and therefore the velocity negative as well. However, the magnitude of the speed would not change, so the overall physical meaning of constant velocity would essentially just remain the same in this case. Zero net force does not mean no forces are acting. In this experiment, gravity pulled downward and the normal force pushed upward, and these forces canceled in the vertical direction. Along the horizontal direction, the rolling resistance was balanced by the marker's initial push, leaving the net force close to 0. As a result, the marker moved at constant velocity even though multiple forces were present. This is the end of my presentation. Thank you for listening.